Welcome, everyone. We are from the University of Washington Aeronautics and Astronautics Department. My name is Anna Hodzik. Our work focuses on simulation-based observability analysis tools for experimental aerospace applications. More precisely, our focus is the development of sensor selection and placement tools to enable high-performance commercial aircraft ride quality as it relates to gust load alleviation. Our ultimate aim is to improve the alignment of control theoretic models with physical test results. We specifically look at sufficient versus optimal sensor selection and placement to characterize the responses of airframes to wind gusts. We allow for the use of a suite of airplane sensors and incorporate measurements across unit scales by balancing the empirical observability GRAMIAN accordingly. Our work is part of a larger objective of wind tunnel testing to improve ride quality and decrease airframe fatigue. Developing advances in sensing and model design capabilities present an opportunity to significantly improve the prediction and control of the response to dynamic gusts in hopes of enhancing ride quality. Increasing use of composites results in lighter and more flexible airframes, which leads to more complex structural behavior. Our results strengthen the argument for wind tunnel testing from both a safety and financial perspective. The techniques and results are applicable in any vehicle domain, providing an opportunity to translate results beyond the aerospace industry. Addressing the optimal sensor placement problem is not a new venture and has been considered in the context of understanding biological, chemical, and power systems. Previous works look at various spectral properties of the observability GRAMIAN to inform the optimization procedure. Although we also exploit the inherent properties of the GRAMIAN, we do not limit the sensor to a single type, but allow for different kinds of sensors. We present an illustrative example using two types of measurements, accelerometers and strain gauges. We propose an avenue for the optimal sensor placement problem as a tool that helps leverage the capabilities of wind tunnel testing and thus balances the inherent experimental cost and complexity of full vehicle flight testing. First, I will discuss the two systems we studied. The first is an open-source aeroelastic dynamic aircraft model developed at UW, which we refer to as FACET. It was designed to address the need for a widely available complete aerostructural model to develop and simulate flexible aircraft dynamics. As it was built around industry-standard NASTRAN elements, NASTRAN is an acronym formed from NASA Structure Analysis. It is fit to perform analyses involving structural mode control, maneuver load alleviation, and gust load alleviation. The model is based on a nonlinear finite element model, but we use the linear time invariant state space model. The state vector is comprised of elements representing rigid body states, angle of attack, and pitch rate, in addition to the modal coordinates of the structural states and their derivatives. The second is a test article developed to support the study of active control for gust excitation, which we call MARGE. The nominal configuration of the test article setup is a half-span aircraft model with 3 control surfaces for use in the subsonic 3-foot by 3-foot wind tunnel at the UW. It is of importance to note that the analytical input-output relationship of the model is augmented with a parametrized system ID method to more accurately represent the physical conditions for the test article. As a result, the dynamically adjusted model for the system incorporates only 2 modes, first wing bending and second wing bending. The first 2 states are angle of attack, measured in radians, and pitch rate, in radians per second. The remaining states corresponding to the modal coordinates and their derivatives are unitless. Measurements include pitch angle, measured in degrees, the accelerations, measured in g's, and the strain values, which are measured in unitless microstrain. The measurement vector contains the sensor locations corresponding to nodes from the finite element analysis. The nodes from the NASTRAN aerostructural model are imported as potential sensor locations, which represent locations suitable for optimal sensor placement. Both FACET and MARGE constrain sensors to lie along either the fuselage or one wing. FACET symmetry allowed us to use one wing for simplicity. Fundamentally, observability describes the ability to map observations back to state space. A system is observable if it is possible to estimate any state from a time history of the measurements. Analytical observability applies to both linear and nonlinear systems. For linear systems, the observability can be represented by a binary value determined by the properties of the observability matrix. The system is observable if the matrix is full rank. We can similarly construct an observability GRAMIAN, which not only tells us whether the system is observable, but how observable or unobservable it is. By studying the eigendecomposition of the GRAMIAN, it is possible to order the states by degree of observability based on the corresponding eigenvalue. The analytical observability GRAMIAN can be approximated with the empirical observability GRAMIAN, which does not explicitly depend on the dynamical model of the system. As long as we can perturb the initial state conditions, the empirical GRAMIAN can be constructed via simulation or experiment. We use simulation in order to run hypothetical studies with sensors at various locations. The system is simulated twice for each state of interest, once with a positive and once with a negative perturbation. The empirical GRAMIAN is computed by designating the delta y's to represent the change in measurement between the positive and negative perturbation. However, depending on the units used, the viability of a measurement can be influenced by its absolute magnitude, rather than its magnitude relative to other measurements. As previously mentioned, we examined 2 different types of sensors, accelerometers and strain gauges. Appropriate scaling must be incorporated into the empirical GRAMIAN calculations in order to properly weight the observation coming from each node and each sensor type. Denoting a vector of observations for each sensor type as yj with a superscript I to denote the perturbation state index, we partition the observation vector by sensor type. Then we quantify the maximum and minimum measurement from the set of runs for that particular sensor type and normalize based on the range of measurement within each type. This way, we avoid an inconsistent mix of measurement units. The difference between the sensor selection and sensor placement problems is the constraint on the number of desired sensors. Sensor selection uses all the nodes and returns the type of sensor that maximizes the degree of observability for the set of all sensors. Sensor placement, on the other hand, returns the locations of the best types of sensors to maximize the degree of observability, such that the constraint on the specified upper bound of sensors is not violated. So let's say there is a wiring constraint on my system and I'm only able to read measurements from 5 sensors at any given time. The sensor placement problem will return up to 5 locations with the optimal type of sensor that maximizes the degree of observability. As we know, the eigenspace of the empirical observability Gramian provides the degree of observability of the given sensor set, but different properties can result in different interpretations of what is optimal. In general, the basic 4 measures are either based upon the smallest eigenvalue, the least observable direction, or the largest eigenvalue, the most observable direction. Maximizing the minimum eigenvalue strengthens the least observable mode and gives a sense of how close the system is to being unobservable. This is a conservative approach as it measures the least observable mode, so in a sense it's the worst-case scenario. Maximizing the trace, or the sum of eigenvalues, maximizes the transfer of energy from each perturbation to the observations, thus increasing the degree of observability. But this metric alone cannot indicate the unobservability of individual directions, as there may still be a 0 or almost 0 eigenvalue. Maximizing the determinant effectively also maximizes the eigenvalues. Similar to maximizing the trace, this metric characterizes the overall observability while favoring non-zero eigenvalues. Minimizing the condition number is useful for estimation problems because it minimizes the magnitude of the difference between the largest and smallest eigenvalues, thus ensuring the observations are not dominated by particular modes or subset of modes. This metric might still result in an almost zero eigenvalue, thus rendering the system practically unobservable. These metrics can be combined to achieve desired results. For example, some applications might not require that all modes are equally observable, but might require that no mode is close to being unobservable. In this case, the minimum eigenvalue is more crucial than the condition number. The optimal sensor problem is essentially a combinatorics problem. Given a set of possible sensor locations and sensor types, the optimal observability Gramian for a combination of sensors is the sum of Gramians for each sensor. A binary activation function, beta, is used which acts as an off-on switch. To formulate the convex optimization problem, we relax the activation variable's binary constraint to a linear inequality constraint. The objective function is a weighted sum of 2 convex functions of the Gramian using the previously defined measures. Note that we allow the solution to return fewer than the maximum specified sensors if additional sensors do not increase the degree of observability. The systems considered here are simulated in MATLAB Simulink environment. For FACET, the sensor suite, which previously included only accelerometers, is expanded to include strain gauges at all specified nodes. The potential sensor locations include a total of 145 nodes. Now moving on to MARGE. In addition to the strain gauges and unidirectional accelerometers already present on the physical setup for MARGE, the simulation model is expanded to incorporate a total of 54 potential sensor locations. For both systems, the state vector contains modal coordinates, eta, which with the matrix of orthogonal modes, or phi, approximate the structural deflections, q. For a conventional wing, it is expected that critical design loads due to gust will be a function of displacements from the first and second modes. Specifically for the MARGE test article, we are looking at flapwise motion for a model that has been mathematically constrained to 2 modes, so eta1 and eta2 encapsulate the dynamics of the system. As such, the states of interest for this work are the modal coordinates. Through perturbations of the modal coordinates, we compute the empirical observability Gramian and characterize the degree of observability for gust observation. The objective function and solution combination that yields the best balance of the 4 measures differs for the 2 systems. Overall, FACET proved to be a less complicated optimization problem. Future work for FACET includes studies requiring state and noise estimation, so the condition number is crucial in verifying that measurements are not dominated by particular modes. We also want to make sure that all modes are observable, so the objective function selected for FACET is a weighted sum of the condition number and the inverse of the minimum eigenvalue. In essence, we first normalize the eigenvalue spread by the smallest eigenvalue, and then minimize the largest eigenvalue of the normalized linear matrix inequality. Attempts to optimize over all 4 metrics resulted in difficulty returning a well-conditioned empirical observability Gramian for MARGE. In other words, optimizing the condition number led to very small eigenvalues, which inherently led to a lower trace and determinant, and thus a very low degree of observability. Due to this fact, the objective function selected for MARGE is a weighted sum of the determinant and the minimum eigenvalue. For both FACET and MARGE, the optimal configuration of sensors is intuitive. In general, the wing shows accelerations that increase from root to tip of the wing, and strain that is largest at the root of the wing and 0 at the wingtip, as bending moment is maximum at the fixed support and 0 at the free edge. The suggested transition near wing midspan from strain gauges to accelerometers is aligned with engineering judgment and the measurements of strain and acceleration from the respective sensors. As the wing of MARGE experiences a gust, the fuselage does not output significant measurements since it is modeled as strictly rigid. Therefore, recommended sensor placements occur only on the wing. For the constrained sensor placement problem, with a maximum of 2 sensors at our disposal, the algorithm advises 1 strain gauge at the wing root and 1 accelerometer at the wingtip, as shown. This figure compares the analytical observability GRAMIAN to the empirical version for the upper bound of 2 sensors from the previous slide. This is for the MARGE case, calculated by solving the Lyapunov equation for the observability GRAMIAN. Since we are interested in observing 2 states, our GRAMIAN is a 2x2 matrix. The eigenvalues of the analytical GRAMIAN and empirical GRAMIAN are well aligned. As the upper bound on sensors increases to a maximum of 10 sensors for FACET and 7 sensors for MARGE, the algorithm increases both the number of strain gauges at the root and accelerometers at the tip. Adding extra sensors results in marginal improvement in the observability metrics, and the optimal value is not improved much as the number of sensors increases. An interesting observation of this is seen here. In this case, the upper bound on number of sensors is the total number of potential sensor locations, or nodes. It is clear that not all sensors are necessary. Measurements on the most rigid portion of the fuselage do not provide much information and are supplementary. The chosen convex optimization problems for the respective systems are shown here for increasing upper bounds on the number of sensors allowed. As seen on the left for FACET, the improvement of the trace and determinant of the empirical observability GRAMIAN greatly increases past 2 sensors, but the surges in all metrics after about 10 sensors are marginal. As previously discussed, the condition number for MARGE actually increases, suggesting that observations are dominated by particular modes. We plan to continue the work on 3 test systems, and are currently working on Kirsten wind tunnel testing for a highly flexible wing. This highly flexible wing can be seen in the video from a previous test run. In addition, our partnership with Boeing allows us to apply the algorithms directly to commercial aircraft. Thank you for attending our talk and showing interest in our work.